Okay. So in fifth week lectures, mostly some simple topics. I mean, almost the basic topics were covered. I hope you have gone through those lecture videos. And some of the topics discussed in week 5 lecture videos, we have actually already covered in our uh, interactive session. But still, we can go through again. So in week 3, uh, videos and week 5 videos, the lectures are about the schemes, numerical schemes, and also how we can establish or uh, discretize different scenarios or different equations. Mostly our flow physics or the problem physics is represented by using some PDEs, partial differential equations. So how these partial differential equations can be discretized, and what all are the different varieties of partial differential equations that we are mostly dealing in our CFD. So all these were discussed in our week 5 lectures. So let's move on to the questions. So first question. In a finite volume method, the integral form of the conservation equation is applied to a control volume. Which of then which of the following statement is true about the discretization of convective term using upwind differencing scheme? So the question is about uh, uh, which of the following is true about the discretization applied on the convective term using a upwind differencing scheme. So the options are: it uses upstream value of a variable for the convective flux. Option B, it is always second order accurate. Option C, it is unconditionally stable for all flow regimes. Option D, it is equivalent to central differencing for steady initial flows. You can inbox your answers. I hope you are familiar with the term upwind scheme and downwind schemes. Actually, if you uh, finding it difficult to follow upwind scheme and downwind scheme, this actually terms proposed by Suhas Patangar in his control volume approach. So, I think in your reference textbooks, the list of reference, there's one book by Patangar. If you follow this book, it is entirely uh, based on this upwind scheme. So, upwind and downwind, that kind of uh, terms is introduced by Patangar, as far as I know. So, this here you have to see uh, the upwind scheme actually is uh, almost is equivalent to the uh, forward. Uh, um, I mean, uh, suppose if you can imagine it as a waterfall or something. Suppose this is our I point. This is I minus one. This is I plus one. So this upstream means upstream, and downwind means downstream. So you can imagine it like something like that. So this upwind scheme can be easily connected to our forward and backward thing using this upstream or backstream of a flow, waterfall or something. That is it. So it is about the convective term. So here the thing is, it uses the upstream value of the convective flux. Actually, yes, it uses the upstream value of the convective flux. That's why the term upwind scheme. In upwind scheme, we use the upstream variables or upstream non-variables for to calculate the values at the required point. It is not second order accurate, it's first order accurate. It is not unconditionally stable. Uh, it is conditionally stable, and it is not central differencing because upwind scheme is a it is similar to our forward and backward schemes. Our answer is option A. It uses the upstream value of the variable for the convective flux. So next question: which of the following statement is not true about the central differencing scheme? So the question is about central differencing scheme. The options are: it is second order accurate for smooth solutions. It can be option B. It can be unstable for convection dominated flows with high Peclet numbers. Uh, Option C is a good choice for diffusive problems with low Peclet numbers. Option D, it is a it is simple to implement computationally. You can inbox your answers. So our options are: it is second order accurate for smooth solutions. Then it can be unstable for convection dominant flows with high Peclet numbers. It's a good choice for diffusive problem in low Peclet numbers. It is simple to implement computationally. So, do you know what is Peclet numbers? Actually, this Peclet number is a ratio of our. It is based on not the We have Peclet number is a dimensionless number similar to that we have in fluid dynamics. Here, it is on for particular cell because we are dividing our computational domain into different cells. So here it is in CFD, the Peclet number is mostly called cell Peclet number. So this uh, cell Peclet number is the actually the ratio of convective coefficient by diffusion coefficient. So this kind of Peclet number, uh, number criteria is uh, required or uh, implemented where we have both convection and diffusion. And that way, here this word convection dominated flows. So that is, we have a flow where uh, in the flow we have the convection and both diffusion is happening. So diffusion means I have already we have already discussed in last week. Uh, that is, the property can the spatial dispersion of a property is called uh, diffusion. How it can uh, infiltrate to nearby spaces due to uh, the inherent property of the solid or some of the conditions existing there. Whereas convection means we have a particular u or velocity which is transporting a property phi across our domain. So we need a convection velocity to transport that particular property. So when there is a flow in which where convection and diffusion both exist, such Peclet numbers are used, and Peclet numbers are required to calculate this which in that particular cell. Suppose we have a region, we have found out one particular cell, and in this cell, which coefficient is greater? I mean, which what is greater? Is that particular region is under the influence of convection or diffusion? So that particular thing is mostly found by this Peclet number, and this by this Peclet number condition only we can move forward with the problem. So the thing is, uh, for central differencing schemes are unstable for convection dominated flows with high Peclet numbers. That's option B is our solution. Going on to the next question. What is the main advantage of using a higher order differencing scheme compared to a lower order scheme? So in our 5th week videos, we have also discussed about higher order differencing schemes. So what is the advantages of higher order differencing scheme compared to lower order schemes? Options are option A reduced computational cost, option B improved stability, option C increased accuracy with fewer grid points, option D easier implementation in complex geometries. You can inbox your answer. So yes, you are right. Uh, the option C, that is, it has uh, higher order schemes can deliver increased accuracy with fewer grid points. Suppose we are using second order scheme or something, then we may have to go for up to 5 grid points. We are using central differencing scheme. We may be using 5 neighbors. So this is I plus 1. Uh, in central differencing scheme, to get a higher accuracy, we will be moving to, in most of the condition, we will be moving to up to 5 neighbors. So this is one dimensional case I am showing. So to get a decent accuracy that we will be having in most of the first order, accuracy will be the terms in I plus 1 and I minus 1. These three terms are used, but uh, to get higher accuracy, we will be using five up to 5 grid points in normal conditions in several different scheme. But whereas if we use higher order schemes, then this almost this accuracy can be achieved with three. I mean lesser. That is the three. And that is the point and two neighbors can itself give higher accuracy. Whereas in lower order schemes, we may have to consider more and more of the neighbors. Next question. When discretizing the diffusion term in Navier-Stokes equation, which scheme is generally preferred? Option A, upwind differencing. Option B, central differencing. Option C, downwind differencing. Option D, any of the above, depending on the flow conditions. You can inbox your answers. Okay, so can you say which one is the diffusion term in Navier-Stokes equation?
That is mu into del square by u by del x square plus del square u by del y square plus del square u by del z square.
Yes, that is our mu del square u, this term on the RHS actually. So the diffusion, the term diffusion itself says that something of a second order. So that is dou square u by dou x square plus, like, second order terms are involved where, so normally these terms we have been calling as viscous terms. Actually, viscous term is here the property or the property getting dispersed due to the virtue of viscosity. That's why it is called viscous terms. Actually, the square terms, when it comes, these square terms are there. It is in a equation. This second order terms, second order partial differential terms in space is what is uh, causing the diffusion. So spatial movement of something. That is a diffusion term. So, if you see for a second order, I mean, this second order, this is second order partial derivative. For that, we will be using central differencing, not forward or up into or down in schemes. So, mostly preferred thing in diffusion cases is the central differencing because it has higher accuracy. So our answer is option B. And mostly in diffusion cases, what we will be using is central differencing scheme. Only we will be using uh, forward or backward schemes at the boundaries, boundary node. Suppose uh, so here and here, these points can actually we can get the uh, front and back terms. That is the immediate two front and back neighbors we can take, but at the boundaries, suppose okay, suppose this is the boundary. This boundary here we can't apply this central difference scheme because when we are considering this point, it is not there. The next term is not there. So either we should go for an implicit uh, implicit application of boundary condition or explicit application of boundary condition. So on either we can use upwind scheme or downwind scheme, or we can go to some other methods. So apart from the boundaries nodes, we will be using central differencing for the diffusion terms. So next question, consider 1D advection equation, that is dou u by dou t plus c into dou u by dou x is equal to 0, which differencing scheme is second order accurate in space but can be unstable for large Becklet numbers. You can box your answer. Here, these are convection time or advection velocity, which we are this particular time is moving this time. So this is transporting this dou by dot time. So this is the convective velocity. So our solution is central differencing because under uh, this problem again we have asked in different form before. At higher uh, Peclet numbers, something called numerical diffusion creeps into it. Uh, so numerical diffusion is something that we will lose the sharp edges of the uh, solution due to our suppose sorry, our solution is something like suppose our solution was a step function, but when using this standard differencing at high Peclet numbers, it will create some numerical diffusion, which will create some our solution will be going like this line. So we will be using this sharp edges, this sharp changes or sharp uh, change in the solution may not be captured well when we are using this standard differencing scheme in high Peclet numbers situation. I think our lectures are yet to reach there, numerical diffusion, but this numerical diffusion part will be discussed later. But next question: when differencing schemes are designed to address which issue? So we have covered different things like conservativeness, boundedness, transportiveness, all those well posedness, all those things. But what the upwind differencing schemes are best used for? So the options are rounding errors, inconsistency, convergence issues, or boundary condition implementation. Which of the following issues is best addressed by upwind difference schemes? You can inbox your answers. So you can also find this upwind schemes means forward scheme kind of thing. So what such kind of scheme is best suited for? So for rounding errors, we know rounding errors means relaxations can be given, or that is more or a convergence criteria, rounding errors, and inconsistency. So first you have to check what is inconsistency. Inconsistency means which is not consistent. So consistency is a uh, condition for good solution. In our fifth week lectures, it is there. So consistency is uh, one of the condition for a good solution. Consistency means consistency gives how much the discretized equation is in agreement with the partial differential equation. How discretized equation is in agreement with our partial differential equation. That is what consistency is. So inconsistency means uh, our discretized equation will be more, I mean, less, it will be in less agreement with the partial differential equation. So is it used for that upwind scheme or convergence issues? So how some particular schemes help in convergence? Boundary condition implementation actually upwind scheme or it will be there is no particular scheme used for boundary condition implementation. It will be chosen on a case to case basis actually. So here the upwind differential schemes or first order schemes are mostly designed to address consistency issues actually. So we already discussed that when we are using central differencing schemes or the schemes which have been having terms from both the directions. So when the discrete equation is having terms from both uh, in the front and back side, so this can cause something called numerical diffusion. So this numerical diffusion can be eliminated by using this one-sided formulas or one-directional formulas. So upwind schemes are uses such that it is transporting in one direction. So such schemes are better suited to prevent numerical diffusion, and I have told you before we can preserve those sharp edges in the solution. Next thing, what is CFL condition? The Coren Friedrich Levy condition is a stability criteria used in explicit time marking schemes. What does CFL number represent? I think this is an easy question. You can inbox your answers. The options are ratio of viscous to diffusive forces. Option B, ratio of time step to characteristic wave speed. Option C, order of accuracy of spatial discretization scheme. Option D, convergence rate of iterative solution process. So what is this CFL criteria? So the answer is yes, you are right. The answer is uh, option B, that is the ratio of time step to the characteristic wave speed. Actually, the CFL criteria is about how, suppose, uh, the equation for CFL is actually U delta T by delta X. So this is how CFL number is calculated. and we will be setting some limits to the values of CFL numbers. Actually, CFL number is uh, limits that how this uh, delta x or delta t should be fixed. So that is, suppose some property phi is being transferred in this grid. So how much time, suppose if we are uh, taking some particular value of delta x here, how much time that particular property or that particular value of this phi will be staying inside our cell. Suppose phi I will be staying inside cell. So if the dimensions of the cell is not uh, in tune with the ratio of the time step, then this change in that particular property's value may not be captured. So we have to fix some CFL value, that is mostly it is not a current number only. The CFL, even if it is CFL number, it is called current number. The criteria is known as current Frederick-Levy criteria. So this we will be setting some particular current numbers for uh, this to attain the stability in a particular scheme. I think in the fifth week's lectures, last video is discussing about current numbers. Next question: in a finite volume method, the governing equation is integrated over a control volume. Which term requires special treatment for accurate representation of convective fluxes? Option A, diffusion time. Option B, source time. Option C, convective time. Option D, all of the above. So from the options itself, you can see this even without knowing itself. You can go for this convective time actually. So, but it is not like that, which needs special treatment. So, any of the times can be affected due to convective fluxes, but where we have a product that is our velocity is getting multiplied with variables uh, in such times where gradients, when gradients are involved, it can be uh, it may not be that complex, but we can use some models there. But when we are having these products of velocity, there we'll have to need some take care that it should be represented properly while we are discretizing such times. So our option C is the correct answer. It is the convective type. Next question: which property of the differencing scheme ensures that it approaches the exact solution as the grid spacing delta x goes to 0? So here the question is about the property of a differencing scheme. We need to find which property of the differencing scheme which ensures that uh, our system will reach the exact solution when our grid spacing delta x will goes to 0. So the options are consistency, stability, convergence, explicitness. You can inbox your answers. Yes, you are right. The answer is consistency. A, because consistency, what we have discussed the consistency earlier itself. Consistency meaning the agreement between discretized equations with the partial differential equations. So this particular term delta x tends to zero. This thing comes if you have if you are remembering the basics of partial differential equations. So it is like uh, when this limits, if you are not the limit theorem, just like limit of some variable phi of x minus phi of x minus 1 or something, phi this delta phi or some step size. This will convert to our dou by dou x or something when this delta phi, sorry, dou by dou phi when delta phi tends to 0, or when the term in denominator tends to 0, then only our limit terms is become PDE. Likewise, this discretized equation is similar to our limit theorem equations. There, if you remember, our condition is like this. Uh, this particular term delta x1, sorry, x1 minus x2 by delta x. This kind of criteria will uh, sorry, I'm making y1 minus y2 by delta x. These kind of things will only change to that, but our differential equation only when this delta x tends to 0 or becomes 0. Such a condition is the basics of a differential equation and partial differential equation. So here intent that they are indirectly asking that particular thing. So the consistency is the quality of the scheme which allows the convergence of discretized equation to partial differential equation or exact solution when the grid is when the delta x tends to 0. Next question. Implicit differencing schemes involve solving a system of algebraic equations for unknown variables at next time step. What is the advantage of this approach? Option A, higher order accuracy. B, unconditional stability. C, lower computational cost. D, easier implementation of boundary conditions. You can inbox your answers. No, it's not lower computational cost. Actually, it is unconditional stability. So, like we have discussed the central difference scheme and upwind scheme, the difference between central difference scheme and upwind scheme. Here also, these implicit schemes are best suited or best given in directional schemes, that is upwind or downwind schemes. So, uh, then again, such schemes provide stability because explicit schemes may create unstable solutions or unstable oscillations. So implicit schemes are best known for its unconditional stability. Next question. In a finite volume method, the integral form of conservation equation is discretized over a control volume. What is the general form of discretized equation for steady state advection diffusion problem? Option A, integral of rho nu minus triple dou u by dou x into dA, dou into rho u by dou t plus dou into uh, lambda dou u by dou x is equal to 0. C dou u by dou t plus C dou u by dou x is equal to 0. D u of I plus 1 minus u of I minus 1 by 2 delta x, which is the generalized form of discretized equation in a steady state advection diffusion problem. You can inbox your answers. Yes, our answer is this one. Uh, Option B. A advection diffusion equation is mostly if it is some u was already phi dou phi by dou t plus u dou phi by dou x is equal to dou square phi by dou x square. So this is generalized equation for advection diffusion problem. But when it is steady state, this term can be taken as zero. Or if you are taking or uh, not exactly in steady state, but if you are taking this the right hand side as zero, the other term as zero, then this is the best suited equation to represent our convection advection diffusion problem. Next question is on Lax-Van scheme. The Lax-Van scheme is a second order accurate upwind scheme What is the numerical stencil used for approximating the spatial derivative in the one-dimensional advection equation? So the options are it is about in Lax-Van scheme. What are the grid points we required to calculate uh, spatial derivative in one-dimensional advection equation? So options are I minus 2, I minus 1, I plus 1, I minus 1, I plus 1, I plus 2. Option C, I plus 1, I plus 2, I plus 3. Option D, I minus 1, I plus 1. So it's about the mostly numerical stencil, meaning which all terms we need. I mean, which are the particular point terms we need to calculate or discretize some particular thing, particular term. You can inbox your answers. Yes, yes. Answer is right. We will be needing these 3 points: I minus 1, I plus 1, I plus 2. This 3 point stencil is required for finding the spatial derivative. Actually, in Lax-Van scheme, is uh, the second order accurate in space and first order accurate in time. So we will be needing these 3 points. Uh, I mean these 4 points: I minus 1, I plus 1, I plus 2. These 4 points in Lax-Van scheme to get uh, second order accurate append scheme. Uh, so moving on to our next question. In a finite difference method applied to one-dimensional Laplace equation, uh, the central difference approximation of second derivative at point I is what? So our options are: option A, phi I plus 1 minus 2 phi I plus phi I minus 1, the whole divided by delta x square. Option B, phi I plus 1 minus phi I by delta x. Option C, phi I plus 2 minus 4 times phi I plus 1 plus 6 times phi I minus 4 times phi I minus 1 plus phi I minus 2 all divided by 2 delta x the whole square. Option D, phi I minus phi I minus 1 by delta x. So the question is simple. We have to find the central difference approximation or central difference equation for second order derivative at point I. So it is for Laplace equation, the same as the one we have seen before, dou square T, if it is in temperature, dou square T by dou x square is equal to 0. In the previous question, we had a function there, q by t. Here it is for Laplace equation, dou square T by dou x square equal to 0, since it is single dimension. So the what is the this is a second order derivative term. So what is the central difference approximation? From the previous lectures, we have seen that it is uh, option A, phi I plus 1 by phi I plus 1 minus 2 phi I plus phi I minus 1 all by delta x square. So this is a, we have 3 points I plus 1, I minus 1. So the forward difference scheme is taking these 2 points, and backward difference scheme is taking these 2 points. When we combine forward difference and backward difference, we get central difference scheme. So central difference schemes has 3 points, that is I minus 1, I plus 1. In forward and backward difference, we only have 2 points, either I and I plus 1 or I and I minus 1, the immediate predecessor or successor, and that particular point. Uh, these forward difference or backward difference terms will only have 2 points, while central difference schemes has 3 points. So if you have, if we can keep in mind, then that itself is simple. So if you see here, this is a forward difference scheme, this is a it's a forward difference, this is a backward difference, and this is higher order. This is a lot of terms here. So the only option with the point I, immediate predecessor and successor, is the option A. So solution is option A. Moving on to next question. Which of the following cases is generally modeled with an elliptic PDE? Again, repeating the question. Which of the following cases is modeled with an elliptic PDE? This question is the options are option 1, steady state heat transfer; option B, propagation of a standing wave; option C, Fick's second law; option D, traffic flow. Try to answer the question. So, what is this elliptic PDE? Actually, this is one particular classification of a partial differential equation or simple partial differential equation. Suppose we can write A into dou square phi by dou x square plus B dou square phi by dou x dou y plus C into dou square phi by dou y square plus d into dou phi by dou x plus e into dou phi by dou y plus f of phi plus some constant g is equal to 0 as a generalized simple PDE. Then we know this is a second order. From the formulation itself, we can see this is a second order PDE. So, it's like same as the way we are solving our quadratic equations, we also have to find the discriminant, that is b square minus 4ac in these cases. And depending on the value of this discriminant, b square minus 4ac, where a, b, a and c are the coefficient of the second order terms here. So depending on the uh, value or solution of this b square minus 4ac, the equation can be divided into three. If this b square minus 4ac is greater than 0, then or it's a positive value, then the that particular kind of PDE is known as hyperbolic equations. If whether b square minus 4ac is equal to 0, then that particular kind of PDEs are known as parabolic PDEs. So obviously the third scenario is b square minus 4ac going below 0, that is less than 0. Such cases it is known as elliptic PDE. So here the question is about how we can solve an elliptic PDE. So for that we have to find how these conditions are generalized or how these conditions are modeled. So this steady state heat transfer, if we have seen just before, the one-dimensional steady state heat transfer we have seen just uh, in the previous question. So if it is in two dimensional, it becomes dou square t by dou x square plus dou square t by dou y square is equal to 0. So this propagation of standing wave, it is given by wave equation. That is dou square u by dou x square plus, sorry, is equal to c. There was an error there. It is propagation of standing wave is in time and space. So dou square u by dou t square, second derivative in time, is equal to c, that characteristic wave velocity, into dou square u by dou x square. So this is an equation in time and space. Then fix second law of diffusion. Fix second law. Actually, fix second law is actually the diffusion equation or convection diffusion equation. Fix second law is given by then again that is in dou u by dou t. Time and space derivative by dou t is equal to d into dou square u by dou x square. So this first order time derivative is equated with second order space derivative, and the last one is traffic flow. Traffic flow is actually a model with Burger's equation. So Burger's equation in one dimension it can be written as dou u by dou t plus c into dou u by dou x is equal to 0. So these are the four equations mentioned here. So from all these, which of the following is showing an elliptic equation? That's our question. So let me. So from our question was, which of the following is forming an elliptic equation? So from these equations, if you have noticed, uh, to get when b square minus 4ac to get less than 0, our only condition is this one. Our only condition is this one, that is dou square t by dou x square plus dou square t by dou y square. Here, if you put this, the coefficients are 1 each. If you put it in b square minus 4ac and try it, it will come below 0. That is the first option A is the answer. So steady state equation, that is steady state heat transfer, that is given by Laplace equation, or del square t is equal to 0. This particular equation, if you check, this will become an elliptic equation. So solution is option A, steady state heat transfer. Moving to next question. In a finite volume method, the Laplace in a finite volume method for the Laplace equation, the integral form is discretized over a control volume. What is the general form of the discretized equation for a uniform mesh? Our options are option A, phi of I plus 1 comma j minus phi of I minus 1 comma j plus phi of I comma j plus 1 minus phi of I comma j minus 1, the whole divided by 4 delta x is equal to 0. Our option B is dou by rho phi by dou t plus dou by sigma dou phi by dou x is equal to 0. Option C, 4 into phi of ij is equal to phi of I plus 1 comma j plus phi of I minus 1 comma j plus phi of I j plus 1 plus phi of I j minus 1. Option D, phi of I plus 1 comma j minus phi of I minus j divided by delta x is equal to 0. Which among the following is the general form of the discretized equation for a uniform mesh for our Laplace equation? Try to answer the question. So from the equations, from the options, we can easily eliminate the second one because it's a partial derivation, partial differential equation itself. So it's not a discrete test equation. So we can just eliminate that one. Then let's see what's our thing. Our we have to uh, resolve Laplace equation, that is dou square phi by dou x square plus dou square phi by dou y square is equal to 0. So how we can discretize this over a uniform mesh? Let the imagine this as a, it's not a uniform mesh, but imagine this as a uniform mesh. So let this is our point I comma j. This is I plus 1 comma j. This is I minus 1 comma j. This is I minus 1 comma j minus 1. This is I, sorry, this is I minus 1 comma j plus 1. This is I comma j plus 1. This is I plus 1 comma j plus 1. This one is I minus 1 comma j minus 1. This is I comma j minus 1. This is I plus 1 comma j minus 1. So if we are for a second order uh, for a second order partial derivative, we can use central differencing scheme. So to use central differencing scheme for x, we will be needing these three terms. So we have just seen what will be the equation for that. It will be phi of I minus 1 comma j minus 2 times phi ij plus phi of I plus 1 j by delta x square. This will be the discretization for our dou square phi by dou x square. Then to discretize vertically, that is dou square phi by dou y square, we will be needing these three terms. So that will become phi of I comma j minus 1 minus, I'll put a bracket here also. Okay. Phi of I comma j minus 1 minus 2 times phi of I comma j plus phi of I comma j plus 1 divided by delta y square is equal to 0. So if we rearrange, and also for a uniform grid, so here it is said as uniform mesh. So for uniform mesh, delta x is equal to delta y. So if you are considering that one, then these both terms, first this term and term can be added together because both the uh, denominators will be equal. So adding it, it will become phi of I minus 1 comma j plus phi of I plus 1 comma j plus phi of I comma j minus 1 plus phi of I comma j plus 1. Then this term minus 2 phi ij is common in both sides. So it will become minus 4 times phi I comma j. So these denominator terms delta x square and delta x square, that both the denominators are same. If we cross multiply that to 0, it will be equal to 0. So if we bring this term here, it will rearrange it to, it will become positive. So our answer is option C. You can check that. So 4 times phi I j is equal to phi I plus 1 comma j. So you can see that is on the uh, predecessor and successor terms in uh, same j values, and also in vertically how it changes. So our answer is option C. This is for a two-dimensional mesh, two-dimensional uniform mesh. Next question: which of the following statement is uh, not true about Poisson equation compared to that of Laplace equation? So first of all, what is Poisson's equation? So Poisson equation and Laplace equation both are elliptic equations. So we have already seen what is a Laplace equation. Okay, before that I will read the options. Option A, the Poisson equation includes a source term. Option B, both equations govern potential flow. Option C, both equations are elliptic in nature. Option D, both equations have uh, similar boundary conditions. You can try to answer the question. So, Laplace equation, we already seen that del square phi is equal to 0, or dou square phi by dou x square plus dou square phi by dou y square is equal to 0. Such a term, such an equation is called Laplace equation. Whereas if it is equal to a source term or a function, it will become Poisson equation. Dou square by dou x square plus dou square phi by dou y square is equal to f of xy. If it's a function, if it is related equated to a function, then it will become the Poisson's equation. So this uh, first option is true, and yes, both equation can govern potential flows. Both are elliptic in nature, that we have already seen. And the option, fourth option, both equations have similar boundary condition. Uh, Actually, the boundary condition will depend on particular problem. How it can have a similar boundary condition but it is not always true that it will have same boundary condition. So our option is option D. Next question. Consider a channel flow simulation. So the flow is happening inside a channel. The pressure field is governed by Poisson equation with a no-slip velocity boundary condition at walls. Which of the following statement is uh, which of the following statements about pressure discretization is correct? So this is for not for velocity, this is for pressure discretization. The options are pressure can be directly set into wall boundaries. Option B, pressure gradient at walls needs special treatment due to no slip condition. Option C, pressure equation needs to be solved only for interior points. Option D, the discretization scheme for pressure should be same as the velocity. We can try to answer the question. So while uh, here this is a channel flow simulation, so most probably about some potential flow condition. Uh, in better condition, we have seen how this uh, velocity is discretized. Uh, Similar to that, we also have to discretize pressure because the flow is happening due to pressure variation. So pressure also have to be distributed. So we have to discretize the pressure equation and have to connect uh, U and P with some staggered grid kind of method, or some other schemes may be used to connect U with P. Then only we can solve our equations. I mean our system. The answer is here. Due to no slip conditions, we can set pressure can be set directly to the wall boundaries. From the wall boundaries, I mean, like as a Dirichlet condition, we can give the pressure on the wall boundaries. From that, we can discretize uh, it with other schemes, and the U and P can be interconnected. I mean, correlated. Next question. Consider a square domain discretized with uniform mesh. So the question is here also delta x is equal to delta y. So the question is the number of unknowns in the discretized equation system, the discretized system of equation for Laplace equation with Newman boundary conditions. BC is boundary condition with Newman boundary conditions will be. So again this is square domain and equation is Laplace equation. Boundary condition is Newman boundary condition. We have to comment upon the number of unknowns in the discretized system of equations. Option A, it will be the number of unknowns will be equal to the number of grid points. Option B, it will be less than the number of grid points due to boundary condition. Option C, it will be more than the number of grid points due to ghost points. We can try to answer the question. So here the first Here the first option is it should be equal to the number of grid points. It won't be equal to the grid points. Uh, and also it won't be less than the number of grid points, because if it will be, you can also think that uh, if the if the number of unknowns is equal to the number of grid points, that is our boundary. Our boundary, there is no boundary values, that our boundary conditions or boundary values are also unknowns. So this condition is not feasible. So in that the option A is giving the idea that we don't know the values at the boundaries also. So such a system is difficult to solve. So then option B is less than the number of grid points due to boundary conditions. So it will be less, the number of unknowns will be less if the boundary conditions are directly given. So such directly given conditions are known as Dirichlet conditions. So if the boundary conditions are Dirichlet conditions, then we know what is the boundary, what is the value of that particular parameter at the boundary. So the number of unknowns, we only have to find out that values for the inside of the mesh. You don't have to find in the outside. So here the question is for Newman boundary condition. So the option C is saying that more than the number of grid points due to ghost points. So our option is option C. Answer is option C. It will be more than the number of grid points due to ghost points. So what is this ghost points? So suppose, so let's say, so this is the uh, our mesh. So at boundary condition, when Newman boundary condition, if here it is given by a Newman boundary condition is given, then we may have to create a virtual cell here. This virtual cell is called ghost cell. So why we need a ghost cell is that here when we are trying to apply the central difference scheme, we will be needing uh, this, we have 1 point. So here we don't have any this value. So what actually Newman condition is giving is uh, phi at boundary, that is there is no change. So phi at boundary is equal to the next thing. So to establish such condition, we may require one virtual cell to start with. So such a cell uh, is called ghost cell. So here we have to solve for both uh, this ghost cell and also the boundary condition. So so to solve for boundary condition, we have to solve for this ghost cell or virtual point also. So the number of unknowns will be more than the number of grid points, because we are inducing this grid points. This ghost grid points here. Okay. Our next question is, in a finite volume method for 2D Poisson equation, the source term f integrated over the control volume and discretized using suitable averaging scheme. The simple true or false question. So in our we have already seen what is a Poisson equation. Poisson equation is dou square phi by dou square dou x square plus dou square phi by So y square is equal to f. So if it is f of x comma y, then this means if we have a mesh, uh, uniform mesh, assume this as a uniform mesh. So here this f is a function of x and y. So this source term is spreaded over all over this our computational domain. This is actually each point is given by x comma y. So when the source term f is uh, integrated, the source term, then we have when we have a source sorry when we have a source term and uh, such as source term when it's a function of x and y, then it should be integrated over because each and every point may have some influence of this source term. So we don't know where it is high or less the source. I mean the heat production or that particular production. It can create source and sinks. So we don't know where the concentration is high or low. So it should be integrated over the control volume and it should be discretized uh, uh, discretized using suitable averaging scheme actually. So the statement is true. Moving on to next question. In a finite volume method applied to the Poisson equation, what represents the source term S, that is S in the discretized equation at the control volume? Options are A, the net flux that is influx minus outflux, the net flux of the dependent variables across the control volume boundary. Option B, change in the dependent variable over time. Option C, the gradient of dependent variable at control volume center. Option D, the boundary condition value at control volume phase. Try to answer the question. We have discussed the same idea in one of our previous questions. So we can, if we look closely, we can simply eliminate some of the options. We know our Poisson equation, that is dou square phi by dou x square plus, I'm writing it in two dimensions, then it is dou square phi by dou y square is equal to s here. So here if you see there is nothing about time. So the second option says change in dependent variable over time. So that symbol we can uh, cancel out because there is nothing about volume. The gradient of the dependent variable at the control volume center. So that will depend on the discretization. That also we can remove. And the boundary condition value at the control volume phase. So actually our solution is option A, the net flux of the dependent variable across the control volume boundary. This actually moving on to our next question. Which of the following statements about the convergence of the discretized Poisson equation is generally true? First one, the solution always converges to exact solution regardless of the mesh size or the differencing scheme. Option B, increasing the mesh spacing delta x and delta y guarantees faster convergence. Option C, a finer mesh, that is smaller delta x and delta y, usually leads to a more accurate solution and faster convergence. Option D, choosing a higher order differencing scheme always improves the convergence. This is a pretty easy question. Try to solve it. Okay, so we can try to solve it from the options itself. The first option says uh, a solution always converges to this exact solution regardless of mesh size and difference in scheme. So that is not true. We can, from our knowledge up to here, we can say easily the solution always uh, depends on the difference in scheme and also in mesh size. So this is wrong. Uh, Option B, increasing the mesh spacing, that is delta x and delta y, guarantees faster convergence. So what is this increasing delta x and delta y? So if you are drawing, this is delta x, delta y, and if you are increasing delta x and delta y, then the meshes become coarser. So a coarse mesh uh, won't give good results. So it may not converge faster also. So it the computation may be complete, but the coarser mesh are not preferable. So increasing delta x and delta y is not our solution. Then moving on to finer mesh, moving on to option C, a finer mesh, that is smaller delta x and delta y usually leads to more accurate solution and faster convergence. That we know. Finer mesh uh, leads to accurate solution and convergence also. But this finer mesh we have to fix it. How finer we need, that we can determine using grid independent studies and all. So this is true. Let's keep there. Then option D, choosing a higher order differencing scheme always improves convergence. So choosing a higher order scheme may not improve convergence. It will be computationally difficult and it won't be easy to converge also. So our solution becomes option C, that we know a finer mesh usually leads to more accurate solution and fast convergence. So we need finer mesh or optimum mesh to be is a, because if we are making it uh, very much finer, the computational cost will increase. Moving to next question. Compared to the central difference scheme, how does the lag scheme, how does the lag scheme addresses the issue of non-physical oscillations in the solution for advection problems? Actually, this we have discussed in one of the previous question, but in another context. Okay, let's see. Moving on to options. Option A, it induces artificial viscosity damping the oscillation. Sorry, read it as numerical viscosity. Sorry for the uh, wrong statement. Read the option as it introduces numerical viscosity damping the oscillations. Option B, it is inherently unconditionally stable. Option C, it requires a finer mesh for accurate solutions. Option D, it is less computationally expensive. So you can try to answer that. Okay. Mm, if you can see, uh, if you can check the options, uh, the question is compared to central differencing scheme, how does last scheme uh, how it is how the last scheme is different. So actually the option B, unconditionally stable condition, this is a characteristic of our central difference scheme. So it won't be the case. We can just uh, cross out, I mean, eliminate the second option. Option B, it requires finer mesh for accurate solution. All the schemes need finer mesh for solutions. So that is not a difference. It is less computationally expensive. That is also debatable. Actually, the answer is it introduces numerical viscosity damping the oscillations. Actually, this numerical viscosity is called another term for what we have already discussed, numerical diffusion. In some texts, it may be this both numerical viscosity and artificial viscosity may be used simultaneously, but uh, actually artificial viscosity is something else. Artificial. In some text, it is both are equated, but actually artificial viscosity later it is something that uh, uh, been used to solve the problems where have this physical discontinuities. That is something like shocks or something. When in shock or something, there is a physical discontinuity. So to overcome that uh, regions of physical discontinuity, some terms of artificial viscosities are induced in our schemes to overcome or solve that issue of physical discontinuity. Whereas numerical discontinuity is numerical diffusion. So numerical diffusion, you have already seen that we are uh, due to the inherent issue of the system. Uh, the sharp corners or sharp features are not captured. So this is actually disadvantages in most of the issue. But whereas this non-physical oscillations or wiggles are there, uh, in some problems there will be this non-physical oscillation of the solution will be there. In such cases, this numerical diffusion can be helpful in damping this non-physical oscillations. So this the disadvantage of the scheme can be used wisely to solve one of another issue. So our option is option A. It introduces uh, again numerical viscosity or numerical diffusion, uh, damping the oscillations. Option, sorry, next question. compared to upwind differencing schemes, what is the disadvantage of Lax-Weintraub scheme? A Lax-Weintraub scheme is actually modified Lax scheme. Option B. Sorry. Option A. It is not inherently second order accurate. Option B. It is more computationally expensive due to complex stencil. Option C. It is not suitable for steady state problems. Option D. It requires knowledge of the flow direction. You can try to solve the equation. You can try to solve the question. So our options are it is no. We can try to check the options. Our options are it is not inherently second order accurate, but actually Lax-Weintraub scheme is second order accurate in both time and space. So Lax-Weintraub scheme is both accurate in second order accurate in time and space. So the first option is not true. This is the wrong option. Option B, it is more computationally expensive due to complex stencil. Yes, actually it's true. It is more computationally complex, computationally expensive because the step sizes are I plus half actually instead of I plus 1 or I minus 1. The lax of scheme uses half step sizes. It's kind of a two-step process. So uh, one step involves two set of equations and it has half time step. So the stencil, our numerical stencil that the grid points or grid conditions chosen are more complicated, which will make the computation more expensive. So it is not suitable for steady state problems. It can be used, even though it is a transient equation, it can be used for steady state problems. But still, this is an ambiguous option. Option D, it requires the flow direction. It requires the knowledge of the flow direction. No, it doesn't require the knowledge of flow direction. We do require the knowledge of flow direction where these numerical diffusions are occurring in the schemes where numerical diffusions can occur. In such conditions, we require the knowledge of flow direction because if the flow direction uh, so this is the mesh or grid. If the flow direction is like parallel to the grid line, then it can create the numerical diffusion uh, cost will be more. It will be intense. So we need to know the flow direction to make the mesh. So in such cases, we have to give some inclined flow or something to the mesh. Our mesh should be generated such that it is not parallel to the our mesh lines. So the in the schemes where numerical diffusions are occurring, such schemes require the knowledge of flow direction. Lax control scheme doesn't require the knowledge of flow direction. So our answer is option B. It is more expensive due to complex stencil. Option C is more of an ambiguous statement, so we can just ignore it. And option B is our actual answer. Moving on to next question. Which of the following factors does not affect the stability of an explicit finite difference scheme? So the question is which does not affect the stability of an explicit finite difference scheme. So first one, uh, first option grid spacing, that is delta x. Option B, time step size, that is delta t. Option C, Courant number u delta t by delta x. Option D, boundary condition. Try to answer the question. So this question is about the stability. Question about the stability of the explicit finite difference scheme. So by stability, we assume the whether the scheme is uh, stable. That is, if suppose uh, uh, will there will be any oscillations like uncontrolled oscillations of the solution that uh, which is happening due to our central difference scheme. Sometimes with central difference schemes, this oscillation can be uh, occur. So such whether such conditions are occurring, or like if some error is introduced. Suppose we are using iterative solvers. So from when going to uh, n to n plus 1 step, suppose I am inducing some error. Uh, I am inducing some error epsilon in nth step. How this error epsilon is changing in the n plus 1 step. So if the this error is getting dampened, or it is getting increased, or it is being unchanged, or such thing, the such thing is called a stability analysis. Such an analysis is called stability analysis. So we can check the stability of numerical schemes by doing a stability analysis or perturbation analysis, where we can purposely induce some error epsilon to our discretized equation at nth step, nth iteration. Then how this error epsilon will be propagated to the predecessing steps. Such an analysis is called stability analysis. So this, as I said, this error epsilon is introduced to uh, our discretized equations. So in discretized equation, there is grid independence, grid spacing is important. So it will affect grid spacing. Then again, for transient problems, time step will also will be there in our discretized equation. So again, this delta t is the change in delta t, or this induced error can be affect delta t. So delta t also affect the stability of schemes. Then if you see, both delta t and delta x is there, and also we know Courant number is a well-defined, well-known stability criteria. So Courant number is also affects the stability. And our last option, boundary condition. Boundary condition does not have any role in stability of the scheme. So it has importance in other ways, but it does not have any role in stability of the different schemes. So our answer is option D, boundary condition. I hope we can end it for today. Thank you everybody for joining. Thank you.